Welcome back. Let's talk about combustion analysis. Combustion analysis is a method to determine the empirical formula for hydrocarbons. Listening to the name, a hydrocarbon is a compound that contains hydrogen and carbon. It can also contain other elements, things like oxygen and nitrogen, the halogens, sulfur, but it will always have carbon and hydrogen. And as you saw when we were talking about types of reactions, when you burn, combust, a hydrocarbon, you generate carbon dioxide and water. And so the way combustion analysis works is that you take your hydrocarbon and you put it into a combustion chamber. And so I've represented my hydrocarbon as CXHY because we know it has both carbon and hydrogen. And then I put ZN for whatever else is in the molecule. But this is my hydrocarbon. I put it in the combustion chamber and you add excess oxygen. And when you combust this hydrocarbon in the presence of excess oxygen, you're going to make water and carbon dioxide. And so these are set up in a way that the products will flow from the combustion chamber through a water absorber and through a CO2 absorber. So in that product flowing out, that water absorber absorbs all the water that was present, and they weigh it before and they weigh it afterward to figure out how much water was generated. And then whatever's left goes through the CO2 absorber, and any CO2 that's present will be absorbed by this CO2 absorber. And again, they weigh it before the reaction is done and after, so they can determine how much carbon dioxide was generated in the reaction. And so combustion analysis allows you to figure out the amount of water that is formed and the amount of CO2 grams that you've generated in this reaction. We can then use this as a starting point. It's like adding an extra step to our empirical formula calculations. So as a reminder, when we were calculating empirical formulas before, our first step was to determine grams of all the elements that were present. Then we converted to moles, and lastly, we determined the mole ratio. What we're doing with combustion analysis is we're using a different method to determine the grams of each of the elements that are present. We're going to use the grams of H2O that were generated to figure out how many grams of hydrogen were present in the original compound. We're going to use the grams of CO2 that were generated to determine the grams of carbon that were present in the original compound. Unfortunately, we can't look at this to determine how much oxygen was present in the original compound because we added a whole bunch of extra. But I'll show you a trick to get around that. This is one of those instances where combustion analysis is not hard. You do have to be methodical with it though. There is an algorithm that you need to follow. You need to understand steps, but you need to follow this algorithm in order to be successful with combustion analysis. I'm going to show you two examples and walk you through this process twice. Please make sure you bring questions to me and make sure you're understanding why you're doing each step, because while it is algorithmic, it's a whole lot easier to remember the steps of the algorithm if you understand what you're doing and why. It's not a black box, I promise. Let's take ascorbic acid and let's say we have a 1.22 gram of ascorbic acid. This is vitamin C. When you combust it in excess oxygen, you will generate 1.83 grams of carbon dioxide and 0.498 grams of water. You'll notice the mass increased because we added oxygen as part of the process. That was not part of our original sample. So those total masses increased. Let's figure out its empirical formula, and then we can use the actual molar mass to allow us to determine the molecular formula, just like we did previously. Okay, here's what you're going to do. You're going to start with either the CO2 or the water, and you are going to write down that value. So 1.83 grams of CO2. Here's where we're going to use a little bit of proportional reasoning. We know that CO2 is made up of carbon and oxygen, right? So in every mole of CO2, the mass of that CO2 would be 44.01 grams. That's 1 carbon plus 2 oxygens. However, the mass of carbon in this same amount of CO2 is only 12.01 grams. And so we're going to use a little fractional, a little factor here to determine how many grams of carbon were present in that CO2. In this case, this is 0.499 grams of carbon. Okay, we just figured out the grams of carbon. We're going to do exactly the same thing with the water. We had 0.498 grams of water. We're going to use a factor to figure out how much hydrogen that is. Well, every water has 2 hydrogens, and so that is 2.02 grams of hydrogen per mole of water, while the entire mole of water would weigh 18.02 grams. And so when you do the math on this, you find that you had 0.0558 grams of hydrogen present. But we know, or I'm going to tell you, that ascorbic acid also contains oxygen in it. And so, okay, that means that if we know how much carbon there is and how much hydrogen there is, we can figure out how much oxygen there was by difference from the starting mass. The original mass was 1.22 grams, and we can subtract the mass of the carbon and the mass of the hydrogen, and that allows us to determine the mass of the oxygen. We've now finished step 1. So all combustion analysis is a different way to find the grams of the elements that were present to start with. Once you've found grams, we're going to finish our empirical formula process. We're going to convert from grams to moles. And then once we have our moles of each of those elements, we can divide by the smallest number to find the ratio. And as we saw before, when you end up with something like 1.33, that's not a whole number, but it is 4/3. So I'm going to multiply all of these values by 3. So multiplying everything through by 3 gives us a 3 to 4 to 3 ratio, and thus our empirical formula is C3H4O3. And this empirical formula has a molar mass that is 88 grams per mole. And because the empirical formula's mass is the same as the molecular formula's weight for that actual molar mass, this empirical formula is also the molecular formula. I know the process is kind of lengthy, so I'm going to do it again. Exactly the same process, just to make sure that it makes sense. So, first step is you are going to use the mass of CO2 to figure out grams of carbon, and the mass of water to figure out the grams of hydrogen, and you'll use that to figure out the grams of the other element, which in this case, for ethylamine, the other element present is nitrogen. And I will note before I get started here, as I look at this problem, my masses are given in milligrams. And so as I start this process, I'm going to convert those milligrams to grams. That'll make it easier to do my conversions. You might have noticed as I'm doing this process for this first piece of turning CO2, that mass into the mass of carbon that was present, that number, that factor that I'm multiplying by, that's really just the mass percent in decimal form. So all the pieces of things we've been learning about recently kind of are coming into play. But it's going to allow us to convert CO2 to carbon, which I've done, and water to hydrogen. And then I've taken the starting mass of the entire sample, subtracted the mass of the carbon and the hydrogen to figure out the mass of the nitrogen that remains. Now we'll take each of these masses and convert them to moles, because an empirical formula is always the lowest whole number mole ratio. I've converted to moles, so now I'm going to divide by the smallest number of moles in order to find my mole ratio. These numbers are very close to whole numbers, and so my empirical formula will be C2H7N. And to determine if that's our molecular formula, let's compare that mass to the actual known molecular weight. Because the mass of this empirical formula is the same as the actual molar mass, this empirical formula, is the same as the molecular formula. That's our process for combustion analysis. Make sure you're being methodical with it. Calculate grams. That's always the same for every empirical formula process. In this instance, you're going to start with grams of CO2 and grams of water, but you're still calculating grams of each element first. Then convert grams to moles, and then find your lowest whole number mole ratio.